Okay, thank you, Adrian, for the invitation. I'll turn this over. Right, 1 second.
Okay. We don't see that on the streams. I thought it was good minimized the top right.
It's good?
This looks good to me.
Okay,
Yeah.
good. Then let's get started. Hopefully all problems are solved. All right, so I would like to talk to you about
It's weird. Look at how it shows on Zoom. It's cutting part of this line. Oh, so stop screen sharing?
stop mirroring.
Yeah, because oh. No, we do want to mirror. I just meant stop screen sharing on Zoom because I think you were screen sharing on Zoom and then connected to the new display, right? So it was formatted to fit your device instead of.
Oh, no screen sharing on.
Yeah. So go back to.
Stop share.
Yeah, you want to mirror your display, definitely.
Like this, the full one. What do you do?
I'm not sure you want to. First go back to mirroring your display.
Entire screen on.
Yeah, start mirroring. And then look, yeah, just to confirm back on the screen. And now try sharing your screen on Zoom. And then you want to maximize it, and we'll see. Perfect. Now we're good.
Okay, good. Good. So I would like to talk to you about recent work I've done on examining experiments with Rydberg systems and with connections to condensed matter physics for a number of different topics. So ranging from supersolids to spin liquids. And so this is a topic that has been of interest to me for essentially many years. So the goal in this field is that you have quite generally some kind of quantum state engineering. So you want to have very good control over singular qubits and essentially then scale them up while keeping things like addressability. So you want to address every single qubit separately, have lots of tuning knobs, change parameters, densities, temperatures maybe. Programmable, that means you can change the interactions, but also for the readout, you would like to have essentially as many observables as possible. In particular, also have in situ information, seeing correlation functions directly. But you would also be interested in RF spectroscopy and analog studies. So the interests in this field for a number of fields. So for instance, for many body physics, this is what I'll talk about today, but there are also interests in quantum metrology, in particular, say, spin squeezing, quantum information, quantum computation. I will not talk about this today. And this is being developed in different platforms concurrently all over the world. Well-known are cold atoms and molecules, but you also have, for instance, trapped ions. You can have photons in nonlinear media, and centers, quantum dots, superconducting qubits. Which one will ultimately win is unclear. They're all being developed. They all have pros and cons. But for us, of interest today will be kind of cold atomic systems with Rydberg excitations. This is an overview slide that I took from Antoine Brouet's slides, but it goes back to a paper by Kate and Hazard. And it gives you a quick overview of where we are today regarding the number of, say, spins or qubits versus the coupling range. So the oldest system would be ultra-cold atoms in optical lattices. They would typically have local interactions or nearest neighbor interactions at best, but you can have hundreds to 10,000 to 100,000 of them. On the other side, you see the trapped ions. They can have anything between dipolar and essentially all-to-all coupling, depending on the phonons. But the drawback is that you typically only get a handful of them, few 10 at most typically. The Rydberg atoms are somewhere in between. You can have a dipolar type of interaction or a van-der-Waals type of interaction. I come back to that. Nowadays, you can have up to a couple of hundreds. And polar molecules would also have dipolar interactions, and you could potentially have more of them. Now, this overview, it will blur over time. People push the frontiers in all directions, so don't take it too literally. What really changed, I would say, this kind of Rydberg physics is the idea of tweezer arrays. And this is something that has been around for 25 years. So that means every atom is trapped in its whole dipole trap. But what really made a change is that about 10 years ago, people could reshuffle where they put successfully loaded tweezer arrays and put them in arbitrary lattices and have good initial states. And they made all kinds of shapes that you see, for instance, in B, C, and D. And every group has its own kind of favorite one. So the Paris group likes, for instance, to make the Eiffel Tower, as you see there. For many body physics, we will mostly be looking at 2D structures. And then we have to say, currently we have about 100 to 200 sites with possible Rydberg excitations. There are ideas around to go to thousands of sites, 6,000 or more. You can find it in the literature, currently not old enough. There are actually also ideas to combine tweezer arrays with optical lattices. There is interesting work by many groups also in this direction. But this is for the future. This is not what we'll talk about today. But the field is kind of booming. There are many ideas and a lot of development. So what makes Rydberg atoms special is, I believe, the most important thing is the so-called Rydberg blockade mechanism. It goes as follows. So suppose you have two atoms, A and B, at a distance r away from each other, and you would like to excite them from the ground state G to an excited state R. Yeah? Then with the Rabi frequency omega, you can excite from GG to GR and RG. So in general, they will be in a kind of a superposition that entangles it. However, an excitation to RR will be essentially not possible because these two atoms, they will repel each other. So a Rydberg atom is an atom in which an electron is put into a shell with a very high principal quantum number. The atom becomes very large. These atoms feel each other. The interaction is of induced dipole-dipole type, so it's 1 over r to the 6th. And therefore, this line, this dashed line, shifts up by a little bit amount, and this makes this transition forbidden. So the Rydberg blockade mechanism is essentially saying if you excite A, you cannot excite B, and if you excite B, you cannot excite A, unless you pay a very, very high energy penalty. This is the thing that we will use in the talk later on. Also note that this Rydberg blockade is essentially the mechanism to make digital quantum real to have a C0 gate. Now, the first many-body experiment with connections to condensed matter physics in this regard, I believe was this experiment done in the group of Antoine Brouet. It's essentially the Rabi term that you have here with the sigma x. There is a detuning here in h bar delta and ni number of Rydberg excitations. And then there is this interaction uij and ij. This is the van-der-Waals type of excitations or interaction that you have between the Rydberg atoms. And this Hamiltonian will then ultimately lead to an antiferromagnet. I will not talk further about this, but I just mentioned it for completeness. Now, the first system we looked at was actually the so-called dipolar XY coupling, something we analyzed together with Björn Sibirski, who I believe is on Zoom. Hi, Björn. And this was an experiment that we analyzed again done in the group of Antoine Brouet that you mentioned here. Now, the interaction is not the one I discussed before, it's another one. Namely, it's as follows. Suppose you have again two Rydberg atoms and you excite both of them. Say an S and a P level had a very high principal quantum number. Then actually what happens is that if you excite this S to the P, you can excite at the same time the P to the S. And so it's a flip-flop on both. And this is now, first of all, a dipolar coupling, not a van-der-Waals type. Like, yeah, you already have the dipolar interaction, so it's dipolar. And so it's we call the resonant, and it will be not Z2, not the Rabi, but a U1 or XY type of interaction. Yeah, so it's a whole different type of interaction. It will be U1 preserving and bipolar. So the experiment that we analyzed went as follows. So the Hamiltonian is shown here on the right on top for completeness. So you have an S plus S minus U1 XY interaction with 1 over R cube. Yeah, so it's dipolar. And let's look at the ferromagnetic case, minus J over 2. And then there is another term, which is a staggered magnetic field, delta I SZ. Now experiment, they prepared the up and the down spins alternating in checkerboard fashion on the square lattice. Yeah, this is by a large delta. And then they ramp down this delta as a function of time to 0. And they hope that this is more or less adiabatic and will pull into the ground state of, say, this ferromagnet. Why is this kind of special? Well, from a theoretical point of view, the spin 1/2 square lattice so has a global U1 symmetry. For nearest neighbor interactions only, you would expect that there is no true long-range order possible at finite temperature in 2D due to Mermin-Hohenberg-Wagner. However, long-range interactions change this picture. Yeah. So if your exponent here, in this case 3, is less than 4, true long-range order is possible. And the way to see this is, for instance, in case of dipolar interactions, you look at the spin waves, and you will see that the dispersion goes as some constant C, which is actually pretty large, times square root K, not K squared or K, but square root K. So this implies that the energy will go as a constant, so ground state energy plus something as T to the 5th, and the entropy will go as T to the 4th. In other words, there is no density of states. There is hence no proliferation of spin waves, and this kind of tells you that Mermin-Hohenberg-Wagner cannot apply. You cannot have long-range fluctuations of the phase of the order parameter. So true long-range order is possible. Experiment, as you see here, as a function of this delta Q and delta F, finds a lobe over which they claim true long-range order. It will say more about this. In blue, you see something on the anti-ferromagnet. I will not talk about this. What did experiment really observe? So they look at the S plus S minus correlation function. Yeah, so they can measure these correlation functions directly between any two sides. And what you see, again in red only, is that you kind of observe a plateau at long enough distances. This correlation function at a value which is, say, 0.11. So it looks like you have true long-range order in 2D, signaled by this plateau. But note that this was only seen after 1 or 2 microseconds. DMRG calculations for the ground state do predict some plateau like this. However, the value is much higher. It's actually almost 4 times higher. So I looked at this with Monte Carlo simulations. So first of all, I do finite size scaling analysis, and I look at the thermodynamic limit. And what I get for the ferromagnet true long-range order is something that looks like this. This is the phase diagram. First of all, you see that when this staggered field is 0, the critical temperature is actually plenty large. It's almost 2 times J. It's very large. And then my value for the critical delta, the quantum phase transition here, is actually twice as large as an experiment. This is simply because the experiment is wrong about temperature. Much hotter, as we will see, than what they thought. I've done the finite size analysis as according to the known theory. So we know what eta is, it's 1. We also know what Z is supposed to be. It's supposed to be 1/2. So you see more or less a nice collapse or something you can extrapolate to the thermodynamic limit. The most surprising thing, however, is if I try to simulate experiment as good as I can with open boundary conditions. So I take the 10 by 10 system from experiment. I make an estimate for how initial entropy would be based on defects in the configuration. And then, the best case would be that's kind of, the temperature should be of the order of 1. But if I do this, as you see here in cyan, my curve doesn't look like a plateau at all. In fact, it looks like something that decays linearly, and it's quite different from the experiment which you see in green. If I wait longer, then kind of my system will slowly heat up due to decoherence effects. But after a time of roughly 8 microseconds, I'm reasonably well in agreement with an experiment. So my understanding is that experiment does thermalize, but it takes longer than what people think. It takes several microseconds. At 1 or 2 microseconds, you are not in equilibrium. And it's currently an open question why this plateau was seen at all. It must be some non-equilibrium effect, but it's certainly not a signature that is possible with the Monte Carlo. Thus, anything that could have been a realistic temperature on a 10 by 10 open system. Yeah.
Can I ask? So T is the time from the start, but could you remind me of your initial position?
This
T equals 0. I mean, yeah. So T. You show the result for 1 minute. T equals 1 microsecond.
Yeah.
8 microsecond.
Yeah. So
what was the system like at 0? T equals 0.
Yeah, at T equals 0, this staggered field is fully on, so it's a
Oh,
Nail state.
You start from there.
And then they ram this down, and this system on 10 by 10 has huge gaps because of the dipolar interactions are pretty large on the boundaries. So this RAM is reasonably well adiabatic on 10 by 10, and after 2 microseconds, you're somewhere here.
But you're talking about the ferromagnet now. So you start from the Nail state, or you start from the fully infrared state?
He started from the Nail state, and it's a terrible idea. They later have other experiments in which they point along Y. You know, when they measure the spectrum, I don't know, I'm not going to show this. They do a much better job if they point all the spins along Y, and then.
Correct.
So there is a lot of initial entropy coming from not a perfect preparation. Okay, so what do we get from this? So I believe this was the first case we could do some thermometry for this kind of systems. The temperature is actually pretty large. It's just below TC. I expected something lower, although gains have been made since then. So these ramps are still not fully understood. Now this paper served the experiment as a lot of inspiration for like spin squeezing ideas. Okay, but otherwise I don't think there is too much to say about this. Now, after we've done this work, Lucas Hohmeier, here shown on the left, asked me, suppose we can combine van-der-Waals interactions and XY dipolar interactions. What can you get? We say, well, then we can make a supersolid. Okay, so it turns out that if you have this type of interaction, so dipolar XY, and you have the van-der-Waals via the usual SZ interaction, and although they have different power laws, to have them compete, you want V to be much larger than T. Yeah? But then there is indeed a case with a phase diagram in which you have superfluid, the usual charge density wave at filling 1/3, the charge density wave at filling 2/3, and a supersolid, pretty much like the nearest neighbor interactions that we predict. Monte Carlo says it's there. Monte Carlo says critical entropy is about 0.2, so it's not totally unrealistic. And so I can only say, if you're an experimentalist, please take a look. Maybe this works. We have computed this for actual interactions. And the trick is that you have 2 different principal quantum numbers. Okay, now let me move on. So for the main part of my talk, I want to talk about realizations of possible quantum or spin liquids with such systems. And it's fashionable nowadays. I asked ChatGPT, what is a quantum spin liquid? Okay, and it said a spin liquid is an exotic state of matter in which the spins do not settle into a regular pattern even at low temperature. This is correct. This would have been the definition 40 years ago. Long-range entangled spins and thus fractionalization. Okay, topological order. Okay, emergent lattice gauge theory. Okay. The importance is new states of quantum matter would have applications in quantum computing and relevant for high TC superconductors. So it knows something about Anderson's RVB. It's kind of a holy grail in condensed matter physics. Yeah? So every year there is a new discovery that is then taken back a year later. But note that we do know that quantum spin liquids exist theoretically in a few exactly soluble models. And then I asked one of those new AI generators to make a picture of a quantum spin liquid, because I've never seen one, and that's what it came up with. And so what it is, I don't know, but that's it. Okay, what I will need is a very simple case of a quantum spin liquid, namely something that is very similar to the Tory code. Are you familiar with the Tory code? So I'll go
We've heard of
quickly.
it in other talks.
So the Tory code consists of two commuting terms. There is a star term and a placket term. Star term, you see it in blue, and you have 4 spins interacting, say, sigma z, product of them. And then you have a placket term, again 4 spins. And now it's the product of the sigma x operators. These two terms commute, and we put here minus sign, so the ground state is found where each of the eigenvalues here and here is +1. Okay. I will say later why this is topological and things like this. So for the moment, let's stay with this. Now, if you add magnetic fields to this Tory code, say one along x and one along z, then the model is no longer exactly soluble, but the topological order extends over a certain range, namely up to 0.33 for voltage x and hz, js and jp are 1. And then there is a phase transition to cases where these terms, these trivial terms win. Yeah, so phase A and phase B are actually one and the same. This is Fradkin-Schenker argument. The dashed line is a first order transition that you get here exactly under 45 degrees by self-duality. And this black point is actually a point that is still heavily debated today, whether there is a higher symmetry or not there. Now, what will be important for later on is that, you know, if you follow this orange line, and you are somewhere here, although you're no longer exactly in the Tory code, there is still the idea of quasi-adiabatic continuation, a la Hastings and Wen. Yeah? So whereas the Tory code, the pure gauge theory can be described with just pure Wilson and 't Hooft loops, if you are here, you need these ideas of fatted loops. It's as if you have to dress your Wilson loops with some local operators. The excitations of the Tory code are as follows. So first of all, the ground state is shown. So the ground state is the equal weight coherent superposition of all closed loop configurations. So any closed loop that you can draw on the lattice, coherent superposition of all of those is a representation of the ground state. Okay, the excitations are as follows. So remember that all the eigenvalues of all star and plaquette terms are +1. So imagine I flip one star term from +1 to -1. Then I could do this, for instance, by flipping this spin. This immediately means that I also change the eigenvalue here. And so I immediately get 2 -1 type of excitations. Now, I can move around this -1 without energy cost. Yeah, the moment that it moves, it restores the +1 here, it restores the +1 here, and it's only at the endpoint that I have a -1. Yeah, so my so-called E anyons, as we will see later why they are anyons, they are deconfined. Yeah? So once I pay the cost of creating an excitation, I can move it around at no energy cost. I can do the same for the plaquette degrees of freedom, or the magnetic degrees of freedom if you want. So I can flip here one eigenvalue of this spin, so which was in the basis, I can flip it, then I get a -1 and a -1 here. And then I can move around the plaquette at no energy cost, so it's again a deconfined excitation. Now, what happens if I braid, if I move, say, an E excitation around an M excitation? And so when I do this, and you see this loop C, then this one goes around this one, then your wave function will pick up a minus sign. Yeah, it's as if it's a fermion. So these are semi-ionic statistics. And one refers to these two excitations as the E excitation in the previous slide and the M anion, E anion and M anion. Now, why is it topological? So suppose you are on a torus, then you can define two types of winding numbers. You can go like this, or you can go like this. Now, in the ground state, you can still have a loop that goes like this. This has a winding number 1. And it doesn't really matter if you look on the figure A or on the figure B, it has the same winding number. So the only thing that matters is winding number modulo 2. So it's 0 or 1. Yeah, so now you can have 4 sectors. You can have a winding number 0 or 1 in X. You can have a winding number 0 or 1 in Y. So you get a 4-fold degenerate ground state on the torus. And it will always depend on the geometry and this degeneracy. Okay, so now for what follows, there was a lot of discussion about so-called Vredenhagen-Markov correlators. Now, so what is the issue? So as long as you have a pure gauge theory, you can just use the 't Hooft and the Wilson loops, and they go as follows. In the deconfined phase, you expect essentially that your Wilson loop decays with a perimeter law. Whereas for a confined phase, you expect an area law. Now, if you have matter fields or at finite temperature, it was argued in the literature that you should ultimately always get perimeter law. You cannot distinguish the two, at least for big enough. Now, for most of what will follow, we will not see this. It will be enough to look at kind of just the closed Wilson. So note that at 0 temperature, you can have true topological order. At finite temperature, you cannot. You can only have some crossover scales. Same with deconfinement for the pure toric code. Yeah, we will not have a probe directly for topological order. It will all be probes of deconfinement. Now imagine that you have a toric code in which there is no plaquette term. Suppose there's only a star term and there are the sigma X and the sigma Z magnetic fields. Can you still get true topological order? And the answer is yes. Yeah, there is a narrow region over the phase diagram taken from this paper by Rahul Sahai et al., in which you can find the toric code in the sense of a true topological order. So, and how is this possible? My plaquette terms were sigma X operators. I no longer have them, but I still have a magnetic field in sigma X. Now you can imagine that there is a perturbative process in 4th order that brings me around the plaquette. So it will go as sigma X to the 4th. So it will generate these plaquette terms, even though they're not originally there. The consequence of this is that the strength between the plaquette term and the strength of the star term is vastly different. The star term will be of order 1, the plaquette term will be tiny, 4th order perturbation theory. The spectrum will therefore kind of show bands. You will have excitations that look as follows. So you could be in the situation in which you have 0 electric excitation, so no E anyons, but you could then still have all possible magnetic excitations. These will cost something that scales with JP, but JP is very small. Anything with a large number of E excitations will be separated by something of the order of, say, JS. Yeah, this will be split off. Yeah, so you get bands, 0 E anyons, 2 E anyons, 4 E anyons, and always combined with all possible ways of having M anyons. Yeah.
Sorry, how are the E anyons related to the forming of the plaquettes, or the plaquettes themselves?
No.
They're not. So what's the significance of the number of E anyons in a given band?
It is just what the spectrum will look like if you have to perturbatively generate the plaquette terms. It's unavoidable if this is due to perturbation theory with some small coefficients. Okay, so now let me take a look at the experiment. So this was an experiment done at Harvard by Semgehini and co-workers. And what you see on the left is the Ruby lattice. It is the Kagome lattice in which the sites are not on the Kagome vertices, but on the links. That's called the Ruby lattice. So it's no longer the dipolar interaction, it's just a Rydberg blockade mechanism and van-der-Waals that we have here. Now the Rydberg blockade radius is chosen as follows. So as you see in figure B, the blockade will be chosen such that you have at most 1 Rydberg excitation in red per Kagome vertex. Okay, so you can see this Rydberg excitation also as a kind of dimers on the Kagome lattice, as you see in the lower part. So this means that the density of Rydberg excitations will be less or equal than 1/4. The expected quantum spin liquid would be the coherent superposition of all dimer coverings on the Kagome lattice, or with missing dimers. The Hamiltonian is as follows. So there is a Rabi term in sigma x, there is a detuning here, and there is this van-der-Waals interaction with the Rydberg blockade. Yeah? So this Rydberg blockade implements my Gauss law. This will be my star term in the toric code. Very importantly, experiment is dynamical. Namely, they start from empty, first ramp up omega, so they ramp up the Rabi term. This will point all the spins along sigma x. When this is done, they will crank up the detuning. When you crank up the detuning, you generate Rydberg excitations. They will feel the blockade. Yeah, so you go from something that is all in sigma x, and then they're going to more and more feel the sigma z and the Rydberg blockade. I will come back to figure E later. Now, the thinking of all of this is actually not on the van-der-Waals model, but on the PXP model. So what you see on the top line is the actual model of experiment, the actual system. What you see below is the PXP approximation. In the PXP approximation, this interaction, this van-der-Waals interaction, is approximated by a value of infinity inside the blockade radius and 0 outside the radius. Yeah, so people write here these projection operators P, they simply prevent that you ever have this situation shown here in the lower left part with two excitations on one vertex. And this has now an infinite penalty, is completely ruled out. In the van-der-Waals case, this is not ruled out. This has an energy penalty of roughly 200, depending on your units. This was analyzed and proposed by Ruben Verhezen and Ashwin Vishwanath. They did DMRG on this. And on the PXP model, the phase diagram is as follows. You have this trivial phase with all the spins along X. Then there is a transition of Ising star type to the quantum spin liquid when the detuning is about 1.4. And then there is another one to VBS, a kind of a solid, but a very strange solid with a huge unit cell, around 2.1. Yeah, the numbers for PXP and van-der-Waals, they slightly differ. It's roughly a constant factor of 2 to 3. Now, if you do DMRG, IDMRG, and you do it for the full van-der-Waals, it turns out that as a function of truncation that you have on your interactions here, you may not find the spin liquid. Yeah? So if your truncation radius is bigger than 6, you do not find a quantum spin liquid. But if it's lower, there is still some radius. Yeah? So this is already a kind of a problem. So the ramps are really key to understanding the experiment. Yeah, so the ramps I already explained. Yeah, so first the Rabi term, and when this is over, they crank up polynomially some strange optimized form for the detuning. Now this is actually smart. Namely, if you prepare all spins along X, it means that this commutes with the weak plaquette term. Yeah? You never have the plaquette term present in the Hamiltonian. It was not manifestly shown. It has to be generated perturbatively, but by preparing a state that is essentially the eigenstate of sigma x, you kind of have something that will commute with your very weak plaquette. The Gauss law is a strong interaction and efficiently project Gauss law violations in the dynamical state. Yeah? So keep this in mind. Now, how did they probe an experiment? They have two kinds of loop operators, namely something that probes for E anyons and something that probes for M anyons. For E anyons, they look at Z loops, yeah, so diagonal loops, and the operation is shown here. So if there is no dimer present, nothing happens. It's on the part facing the hexagon, it's a 1. If it's one of the sides of the triangle that stands up, they flip the minus sign. Sorry, they don't flip, they stay, but get a minus sign. Yeah, this is essentially counting the number of Rydberg of Gauss law violations. And so ideally, this should, by construction, be -1 if its expectation value is less than -1. That means there is some Gauss law violation, so you're probably missing dimer excitation because the detuning is clear. Shown in figure C is for loops of different length, 1, 2, 3, and 4 hexagons, the closed loop Z operator, and you see something that is non-zero. It has a reasonable value, 0.1, minus 0.2, minus 0.5. And then the relevant regime will be delta from roughly, say, 3.5 to about 4.5. And if this is an area law, it will, if this is a perimeter law, it will be a good use. But clearly, there is something that is not zero. So the plaquette terms have to be generated perturbatively. Essentially, you need to flip these kind of configurations across hexagons. But this is only one term. This process will go as omega to the sixth sort of perturbation theory, divided by delta to the fifth, and the prefactor is 0.1. This scale is tiny. To probe for the deconfinement in the off-diagonal sector, Rydberg came up with the X loop. It's, I don't know if I have his action. Oh, it's here, sorry. So it's here, yeah. So if there is no dimer present, you add one with a factor -1, and you flip on the upside sides of the triangle. They have a very ingenious way of measuring X loops. I will not talk about this, is really clever. But the result is as follows. Yeah, so for loops of length 1, 2, 3, and 4, you again get a nice scaling. Note in particular the range 3.5, 4.5, where it's again non-zero and actually looks good. The values are somewhat higher than for the Z loop. So
what is that curve? I mean, how is that obtained? Is that experiment or?
This is experiment. This is experiment, and this is this, and they have this protocol of measuring X, which is changing to Z and other Rydberg blockades and back. This is okay. Now, in principle, I should talk about Friedel-Hagen-Markov. I will not for simplicity. I think it will not add anything, and I have to save a bit on time. Now, they again took these closed loops from before, and they raised them to some power. So for the Z loop and the X loop, they rise them to the power 1 over area or 1 over perimeter for both cases. And what you see is that for the X loop, they get something that apparently hints at perimeter law scaling, whereas for the Z loop, they get something that is initially definitely area law. And then they claim that there is one point where it's not following the area law, but I disagree with the explanation and experiment there. I think this is an anomaly. I think there is area law scaling, nothing else. Now, how can we understand this? Actually, there is a strong connection to timer models on Kagome work that was done in the late 90s and early 2000s. What you see here is a figure from the paper by Zeng and Elser from 95. And you again see timers on the Kagome. And what you see here is a transition graph. And there they show that if you apply this transition graph to this configuration, you will go into that one. Yeah. And these transition graphs, they are essentially closed loops that you can draw on the David star. Okay, it turns out there are 32 different loops you can draw on the David star and combine them. What Ms. Guic et al. Have shown is that this construction can be done independent of the initial state. Yeah? What they actually show is that these 32 loops form a sigma x degree of freedom. Yeah? So in other words, there are two classes, and you need to apply these flips to go from one to the other. So it behaves as an effective sigma x. And this builds something that is essentially local and commuting. Local in the sense of well-defined on the David star, and commuting. CF Tori code. Now, pretty much our quantum spin liquid regime in the PXP model, where we think it exists, is akin to this kind of asymmetric Tori code. And it will also connect to what I just said. So imagine I do Monte Carlo, and my spectrum is the one shown in blue. Then my temperature, it will never reach this tiny blue scale, which is 10⁻⁵. Even if I do temperature 1 over 100, I will be somewhere where the dotted line is shown. Yeah? This gap is the ditune. So what will happen is if I do Monte Carlo here, I mean quantum Monte Carlo here, I will be in the ground state with respect to the E anyons. There will be 0 E anyons here, but I'm infinitely hot with respect to the M anyons. I get all possible excitations in an incoherent way of this lowest band. If I were able to get within the band, I would see that this gaps out. Yeah? I would be able to see this fourfold degenerate ground state separated by something of the order, a fraction of JP. But this is so tiny, I just can't do it. Now, how many states will there be in this band? It's roughly the number of hexagons, but it's not exactly the number of hexagons, it's the number of hexagons plus 1. It's number of hexagons minus 1 plus 2. But the number of hexagons is the number of sides divided by 6. Within this picture, this VBS state is kind of irrelevant. The VBS is a resonance within this lowest manifold that really does not affect what happens at higher temperature. If you do exact diagonalization, which is always a good thing to do because ED never lies, and you do this for like PXP models, and I do this on 2 by 2 unit cells, yeah, so I have 24 sides, 4 unit cells, so 4 plus 1 is 5, 2 to the power 5 is 32. I see indeed that there is 32 states with very low energy split by something of the amount delta, and then many states. And this holds everywhere in the PXP model. I mean, over the relevant regime of delta at least. Now, if you go to the PXP plus some van-der-Waals scale, this structure kind of also exists in the relevant delta regime, but not for high delta. If I go to something that I would say, this mimics the full van-der-Waals, yeah, so it has some nearest neighbor with the true value, not infinite 200 NSL, then actually you still see that there are 32 low-lying states, but they get shape, more shape, and here it's gone. And I think this is a strong indication that ultimately you will not be in a quantum spin liquid for the van-der-Waals. So my claim is that the structure of Semgehini et al. Connects as a function of infinite 1 over delta, so 1 over the tuning, away from the dimers to this case with missing dimers, and that is the quantum spin liquid, but that the structure that they have in sigma x is still there. And the reason is quasi-adiabatic continuation. And it turns out that this is exactly the X loop on one hexagon that Rydberg constructed. Yeah. So we now understand there should be a local and commuting structure in this problem. What does Monte Carlo tell you? So first of all, we look at always on the left PXP and van-der-Waals type of interactions on the right. And we look, temperature range will be up to beta 100 in units of Rabi frequency. To see the transition from quantum spin liquid to the trivial case, yeah, it's Ising star, but there is no local order parameter. Yeah, this is always a topological transition. So what we look at is a finite temperature generalization of the fidelity susceptibility, and indeed you see some peak around 1.4. Yeah, so there is a regime that is trivial here, and there is a regime that is different that I label here as classical spin liquid. CSL is not chiral, but here stands for classical.
Could you remind me the definition of fidelity, susceptibility, and finite temperature?
Yeah, so what we use is an integral. What we use is word, I think there are several people who have done this definitely one way. 0 to beta, it's tau, h1 of tau beta. And h1 has to be the perturbation. In this case, it's driven by the tuning, so this is essentially sigma z. And that's diagonal. And this is easy to evaluate because this one is diagonal in the computation case. This is the tau interest.
Thank you.
If you do this for the van-der-Waals type of interaction, you again get a trivial region. You get again some peak, yeah, separated from some classical spin liquid. Then there is a bump, and this is obviously on the right a paramagnet. And this bump is a crossover, it's there, but this will be paramagnet for very large delta, more than 7. Now, let's move to the entropy. So what does entropy tell us? So again, on the left, you get...
Sorry, what do you refer to as a classical spin liquid here?
Yeah. So with classical spin liquid, I refer to this picture here where my temperature is here. So I am in the ground state with respect to one sector, but infinitely hot with respect to the other. So right. I'm in other words having an incoherent superposition of all possible configurations, not a coherent one. So entropy as a function, entropy per side as a function of temperature. So while you cool down, and we do this for different detunings. Yeah? Recall that the transition is around 1.45 to 2.1 for the quantum spin liquid. And what you get is always the following. You start cooling, 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 and you always hit a plateau. You always hit the plateau at exactly the same value. In the trivial case, you will ultimately see that we do find the ground state, entropy goes to 0, whereas otherwise we are unable. We are simply not good enough. The surprising thing is that this plateau is independent of the value of delta. Yeah, I changed the detuning, but the entropy is the same. Now, this value is exactly log 2 over 6. So in other words, it's exactly the number of hexagons. So in other words, it hints exactly at the existence of a local and commuting spin 1/2 sigma x degree of freedom per hexagon that I'm unable to see at lower temperature. If you do this on the van-der-Waals side, you get something that is roughly similar. Yeah? So you cool and you get over the relevant regime 3.5 to say 4.5, 5.5, something that approaches a plateau, two-scale behavior, but your value is not pinned. It is changing. Yeah? Recall the spectra that we've seen in ED. This is what's going on. Yeah, but there is a plateau, and in most cases, we are not sure we reach the ground state. It's incredibly tricky. It could be that there is a simple structure. It could be there is not. What about the Z loops? So Z loops has a function of detuning for PXP for different loop lengths. These loop lengths are not the same notation as an experiment. What you see here is, so this is 1 hexagon, these are 4, these are 9. So it's 4 times 4, 5 times 5, 6 times 6. It's much bigger than an experiment. And you get this, and this is a super nice perimeter law behavior. Yeah? In the trivial regime, it's essentially 0, but anywhere else, you get perfectly nice perimeter law behavior, even beyond the putative quantum spin limit. I'm here always in the ground state for that sector, so it's definitely perfect perimeter. If you do this on the van-der-Waals side, again for beta something of the order 100, you again get essentially 0 in the trivial case. Then you get something that is actually quite nice. You get something that is again perimeter loss like scaling up to maybe 4.55, and then it goes away. This is the paramagnet for sure. Or maybe VBS, I don't know if they are cold enough. So what's going on in experiment? Yeah, so experiment is ultimately dynamical. And now you can take 2 points of view to explain. Let me try to explain everything in terms of E anyons. So you start by preparing everything pointing along X. Right? This is the ramp for the Rabi. That means you start with something that has a lot of E anyons, and you remove E anyons. At some point, you are very close to the transition. You're not able to do this adiabatic anymore, so therefore you will have a number of E anyons remaining. They will be there if you cross the transition. The number of M anyons will be essentially 0 because of your very nice preparation in sigma X, and it commutes with the blockade. Okay, so what happens is, the moment that you cross the transition, you have a number of E anyons. That means that you're no longer in the ground state, but you will have a population of these states shown in red. They will be magnetic ground states of high populated bands. They will be actually high in energy. Whether you have this one and even more, I don't know, but you certainly have a lot of this one. Rahul, Ruben, and Ashwin came up with a picture of spin lakes. Yeah? So you could define a typical length scale between the E anyons in which you have a kind of a quantum spin liquid type of behavior, which they call a spin lake, but you never know if it's a spin lake or a puddle. It all depends on the number of E anyons. Yeah, so the ramps are really such that you're instantaneous with respect to the magnetic ground state. Look at these scales, and you're adiabatic in the electric channel. The implications of this are as follows. So it implies, if this picture is correct, that the electric channel is in quasi-equilibrium in experiment, always. That the magnetic channel will thermalize fast, but is ultimately, after the Kibble-Zurich, not in equilibrium. And this will thermalize on the scale of several microseconds. Locally, and for a fraction of a microsecond, you have a kind of a dynamical state that will have a reasonably high topological entanglement entropy, but never exactly pinned and log 2, and it will not scale. If you increase system size, if you do longer times, this number will go down. All of this could be falsified in experiment or with state-of-the-art dynamics. And I also expect the coherence effects to matter for longer duration of experiment. Okay, so as I already said, there is this picture of a spin lake, which I think is theoretically sound. The question is only, is it seen in experiment, yes or no? So first of all, let's put these claims to the test. So if the electric channel is in equilibrium, the simplest observable would be just the number of Rydberg excitations. Yeah? So when we look at the number of Rydberg excitations, and for ease of calculation, I have to take a cutoff that is big enough, say 5. So in experiment on the right figure, the data are shown with the blue squares, and different temperatures, 4, 6, 10, and 20, are superimposed. There is no reason why you should have the same temperature everywhere. This is not the case. Temperature could change if you change the amps. But there is something indeed, over the range 3.5, 4.5, where you reasonably well reproduce something quasi-equilibrium. I cannot really say what the temperature is based on this. I can only give you like an upper bound. Yeah. So temperature will be probably not more than 0.2, 0.25. In experiment, there is something strange. If you look at the number of Rydberg excitations, at some point it exceeds a quarter. This is due to van-der-Waals PXP, but they have essentially too many of these kind of guys. These are in this green curve in the lower part. There are too many of them. This is never reproduced in the numerics. So what happens if you look at the Z loops in experiment? So on the left, recall these two figures. Yeah? For the Z loops, closed loops, this was the scaling, and they claimed this was area law. On the right, you see for full van-der-Waals interactions and different detunings, namely 3.5, 4.5, and 5.5, the behavior on Lin log scale of those Z loops. And what you see is that if you're very cold, these are the curves in beta 40, beta 30, beta 20, you essentially get a very nice perimeter law. And if you get a little bit hotter, you see that for short loop lengths, you still are kind of linear. Yeah? So it's a perimeter law, and then it curves down, area law. Yeah? So you see the crossover scale. Yeah? So this would be the spin lake with some goodwill, and this would be the classical or hot liquid. If you're really hot, like in the black case, you just get a very quick decay area law like. Yeah? And this is seen for all the detunings. Now, the numbers in experiment, if you look at those, they're actually much closer to the black line. So probably experiment is closer to a quarter. Temperature is closer to a quarter, at least on small enough distances. But see that we have never a case where you start with area law and go over to perimeter. We never have. Okay, now, there have been some results on time-dependent variation of Monte Carlo from Giuseppe Carleo's group. There is more results coming from Harvard soon. Let me skip this and jump to the conclusion. Yeah, so there have been, I think, exciting new physics with Rydberg atoms, tweezer arrays. I talked about long-range interactions Rydberg blockade model. I believe this is a realistic route for a defect-induced lattice supersolid with numbers that make sense. Currently, I see no exceptional evidence supporting the exceptional claim of a quantum spin liquid. I believe there is a very important role by quasi-adiabatic toric states, local and commuting resonances on the David star building magnetic degrees of freedom. The quantum spin lake, spin puddle picture should be applicable. However, current experiment hints at a puddle and not a lake. And with this, I thank you for your attention.
All right. Do we have any questions online or here? So,
Yeah, very basic question. So for those of us less familiar with the torque code, could you just remind us of the definition of Z or Z?
The loops?
Yeah.
So you make a path.
Yeah.
And then whenever you have a triangle, you have to apply this operation. Then you take the product and the expectation.
Gotcha. Thank you. Very clear.
So let me see if I got it right, but what you're saying is that there are a lot of basically solid is coming from the quantum state preparation, and the system may not be thermalized.
Oh, the system is certainly not thermalized. The system is certainly dynamical.
Because your measurements are typically in equilibrium, right? So at some temperature, but they differ significantly from your curves, right? So
I can Monte Carlo only can give you an equilibrium
Right.
picture. Yeah, this is,
Right.
but given what experiment is, given the nature of these ramps, you must be necessarily in equilibrium for the electric channel, and you are certainly not in equilibrium for the magnetic channel. But because of the separation of scales, there is also a separation of time on which these processes work. And you should be able to say something about equilibrium for the E channel before the M channel ultimately terminalizes on much longer scales.
Are there channels for these excitations to thermalize longer timescales, or once you create like
So what dynamics will tell you,
2 charges, 3 charges, they just
what dynamics will tell you, and there is already data that, but it's not published, is that the E anyons are instantaneously in equilibrium. They never, you see no change if you introduce a whole time. The M anyons, I mean, this is like, Kibble-Zurich type of mechanism. You will have, after the initial quenching, you will have a period of coarsening, and then ultimately they have to slowly thermalize. Yeah, so you will see that they are there and then slowly terminalize. But it will be several microseconds.
all right. Let's think about it. 1 or 2.